Assalamualaikum warahmatullahi wabarakatuh, everybody. Welcome to the first video of CSE T30 numerical methods, first conceptual video. Even though it's an introduction, we already had an introduction video, so we're gonna learn true values over here. That's a topic. So let's start. We're gonna skip a lot of things over here, so you might want to pay attention, and you don't have to worry about the slides that we skip. I skip, that is. So let's get the idea of what a numerical method is. Let me get my weird pen, and which color should I pick? Brown. So to solve mathematical equations analytically means the formulas you know. For example, f of x plus h minus f of x by h. You do recognize this one, right? Similarly, a square equals a plus b, a minus b, you know, all those formulas. We get some values from these formulas, you know, physics and whatever, and then we make some assumptions. For example, if you have 79.925, then we assume that it's 80. Then for certain mediums we assume stuff. For example, for 25 dB we assume that the density of water is this, the melting point, boiling point, sometimes under certain conditions we assume stuff. However, when it comes to numerical methods, as you can see, that we actually take a different approach with that. And those assumptions that we do, some problems are such that you cannot solve with those assumptions or maybe those normal analytical formulas. Well, now why is that? We'll get to that. So before that, let's go to the slide below. Now you know all these different kinds of equations from Math 110 and Math 120. You know them. Okay, so here it is, numerical computing. What on earth is this? An approach for solving complex, this is the key word, complex mathematical problems using only simple arithmetic operations. The approach involves, in most cases, formulation of mathematical models of physical situations, which is very crucial for numerical methods. Very, very crucial, because your situation will determine your formula. In different situation, you will use different kinds of formulas. So mark this. It requires development, analysis, and use of algorithm. Development, that means it's not there in the books, just like F equal to ma and the other formulas. You will have to get it on your own. Analysis, you have to analyze that if this is the correct formula you want to use or you need. And of course there's algorithm. Just because you have the formula doesn't mean that that is correct or the way it has been created is okay. So the algorithm is also a fact. Algorithm is a systemic procedure that solves a problem. You already know that from CSE 221, or you will be knowing that from CSE 221. Its efficiency may be measured by number of steps in the algorithm, the computed time, and the amount of memory, and the time required, which is not written over here. Oh, it is written over here. This is actually time complexity and space complexity that we do in 221. Anyways, now you know that why it is CSE 330 instead of Math 330 or something, you know, because numerical method is something that we need for computing. In fact, it is called numerical computing, because computer doesn't make assumption, it works, it does the deal, right? So that's why we are learning numerical methods. Now if you still don't understand what numerical method is, you'll get to know it very soon, inshallah. So don't worry about that. Let's move on. Advantage of numerical methods, not so necessary, but still I'll walk you through this. So the major advantage of numerical methods is that a numerical value can be obtained. You are not making it analytical. And one of the crucial thing is there are many problems that have no analytical solution. In that case, you have no choice but to make a method of your own, and that is numerical. Then again, there is a mathematical operations that required are essentially addition, subtraction, multiplication, division, plus making comparison. That means very simple operations. You don't like you do this stuff, you know, dx equal to like tan inverse something, then inverse x, and then you root it, and maybe then you integrate. I don't know. It's very simple. It is important to realize that solution by numerical analysis is always numerical. By that, I will show you. Analytical methods, on the other hand, usually give a result in terms of mathematical function that can be evaluated for specific instances. This is something that we already do, or we did in Math 120 and Math 110. Okay, where were we? Okay. Now this is an example. For example, this is how you get the roots from a second order polynomial equation. But if it was a fifth order, you know, of ax to the power 5, then this won't work, right? Because this formula that then becomes invalid. So these are some situations where you really need a numerical method, because you can't use this formula. That's a little example. Anyways, now these are the actually course contents. You can kind of say that these are the course contents that we'll be going through, inshallah. This is not so necessary. Just you need to analyze, you need to think, and then you need to make it. You can read it on your own. It's not so necessary, believe me. Okay, now this is an important thing. So what is numerical computing? As promised, I'm going to tell you now. You may have a physical problem. For example, you want to count a baseball machine, and after how many minutes after how many seconds each ball is going. And then you have mathematical formulas. Okay, per second this, per second that, and its speed is this. These are normal mathematical terms, and this baseball machine is a physical problem. You join them together and analyze and come up with a formula of your own, which will be your mathematical method. Normal. Then you use, this is actually a hypothesis, you didn't make the formula yet. Then you formalize that with addition, subtraction, division, multiplication, and then you make up your numerical method. But it's still a formula, so you need to implement this. And how do you implement this? Using a software. Obviously, you will need even if it's a calculator you made up. Suppose you made up a new calculator. It's still at the end of the day a software, right? And then you see, okay, your result is having delays, or maybe you're pressing the result button and it comes after 1 minute. That means you need to improve your algorithm. Anyways, after that you will have some ideas about your algorithm, and then after the final work touch, you will get a solution. Now when you're getting solution, you have to check whether it's right or wrong. So that's the validity. If it's wrong, then you have to restart the process. You probably had some errors, which we'll be doing now, and if you are correct, then that's your application. Oops, sorry for that. So that's the flowchart, and guys, you need this. This is important. Okay. Now, accuracy in numerical analysis. We already know what the term accuracy is. All we need to know now is how it's related with numerical analysis. As you can see, numerical analysis is an approximation, but results can be made as accurately as desired. Errors come in a variety of forms and sizes. We'll do that, so let's skip that for now. Data conversion and round of errors, that's also an error. Although certain errors are not eliminated completely, we at least know the bounds. That's also an error fact, so I guess it's better to go to the error section. Say hello to the error section, and let me get my pen, and since this is an error section, I better use red. So you have various kinds of errors. Let me start with the easy ones. For example, this one, missing information. That is clearly your own problem, man. You're trying to come up with a model, you're trying to work with a project, and you're not careful about your information, or maybe it's missing. That's completely your responsibility. So this is a very normal error. And then there's human imperfection, like you thought that this is binary, so you added 1 plus 1 and you got a 0. Why did you get 0? And other problems like I need to eat pizza, so I can't do that now. Or maybe you're delaying, or maybe you, instead of adding ABC, you added CAB or something, you know. So these things happen, and that's human imperfection. That's because we are, what should I say, not attentive, or maybe not paying attention, or maybe not serious. We make errors. Or maybe when it comes to some specific values or little values, we have some limitations, and we do have a matter of patience, you know. So these two are very easy errors. Now let's come to the real deal errors. First one is measuring method error. You can kind of guess this. So you had a ruler and you were supposed to measure that rope, and now you're such an idiot that we got, oh, not you, probably someone who's such an idiot, he got a data error. For example, it was 5 meters, but he got 4 meters. That's data error, or data error, whatever you call it, which is a part of inherent error, which kind of means input error. Input error. So if your data is wrong, then your input, that's obviously your input, right? You will input data. At the end of the day, you will input data. So that's wrong, so that gives you an inherent error, which another type is conversion error. So you had this data of centimeters, but you forgot how to convert centimeters to meters. So your program had the wrong algorithm, and so the conversion was an error. Or maybe your data type is not right. You were supposed to send integers, but you sent a string. Hi, that cannot be converted, you know. So that's another inherent error, which is also an error of the computer machine, unlike this one, which is a measuring method error. Okay, now we have some numerical errors. Now what are numerical errors? First comes round off error. I kind of showed you this already. So sometimes we always do this, you know. 79 point. Now we can do two things to this. We can floor it and we can seal it. What? You want to floor and seal? What are you talking about? So flooring will make it 79 and sealing will make it 80. Okay, but even though we did this, just because you don't want to write a dot and those 2 digits, these can cause some serious error in a machine, especially in robots, even in programs, and not to mention games. So this is a very serious error for them, even if it's not for us. For you, it's like great, and if it's a grade, you know, marks, then you better, like, even if it's 78.58, you know, I want 8 to come over here and put a 0 over there and remove everything. That's what you would want, right? That's not the case with the computer. And now the last one is truncation error, which is actually the fact that sometimes we make assumptions, like I told you in the beginning of the video, and that also itself causes errors, which are numerical method errors. If you make assumptions, you are bound to get errors, because computer believes in perfection. Anyways, moving on to the next one. Now there's some some modeling errors. I already told you what this is, but still, if you want to see, while developing a model, you can make errors. For example, you don't know about air resistance, so you can assume this. Okay, it's should be from the left, or maybe it would be from the right, or maybe it from the front, or maybe from the back. You're assuming that, but that's not the case. It could be from anywhere, and it can even change. So it's not possible actually. So that's a modeling error. And then you can have inherent errors, input errors to be exact, and then numerical errors. I'm not going to discuss this because you really know that. I already discussed that. As you can see over here, I showed you this. Okay, blunders. And look at these varieties of human errors that we can make. Lack of understanding the problem. No matter how many times you explain to this guy, it's like, I don't understand. Wrong assumption. 2 plus 2, 22. Those guys. Overlooking of some basic assumptions required for formulating. So this guy is such a genius. He knows everything. Okay, if light travels and this happens, this happens, this happens, everything is fine. But he's forgetting the fact that if there is some alternative solution, for example, you may do that with water. Everybody doesn't know about that experiment, so it will take a lot of time to talk about this. Okay, there are some cases where we may forget, especially in experiments, scientific experiments. There are some cases where some people are so genius that they forget some really common facts. Okay, if we do this, we'll do advertising. So you get this awesome restaurant and you want to do advertising, and it's a beef, and you're going around a temple advertising a beef restaurant, something like that. They won't like that. In fact, it may get the opposite result. It could be offensive to them, something like that, But that's so. We add 10 types of masala, we do this and we do that. You're overlooking some basic fact. You're in the wrong place, guy, man. Or I don't even know. Temple is for, yeah, maybe it's temple. Whatever. You got the idea. Mistake in data input, wrong guessing the initial value, making mistakes in computer program, and so on. These are blunders. Okay. Next. Okay. Now we have reached an important topic, significant digits. So what are these? The name kind of gives away what they are. They are significant. So let me show you some significant digits. So you have 2, 7, 4, and without one of them this number will change. If you remove 2, it becomes 74. If you remove 7, it becomes 24. If you remove 4, it becomes 27. So these 3 are significant. Same over here. Now you may say, okay, the numbers after decimal are irrelevant. No, they are not. If you remove them, the value changes. And there could be certain situations where you would want them to stay this way. For example, quizzes and stuff like that. And then this one also, 4 digits. Okay. So that's the idea. You please notice the fact of figures and digits, and all non-zero digits are always significant. So none of them are 0. So that's your rule 1, by the way. That's the rule 1 for significant digits. Number 2. All zeros between significant digits are always between. That's the keyword over here. Between. So you have 0 over here, 0 over here, 0 over here. So this is not between 2 digits, significant digits. So this one will give you 1 only. But this is between 2 significant digits, 4 and 5. So this one will give you 3. This one will also give you 5 because it's between 2. Sorry about that. And so will this one. Except this one. All of them are right. So that's your rule 2. Rule 3. All final zeros to the right of the decimal are significant. So if you have a 0 at the right, they are significant. So 32.0 is not the same as 32 when you count significant figures. 19.000 is also significant. Now you may say, hey, you had 800 and there you said that this is one digit, then why are you counting these 3 zeros? Well, you have to see to the right of the decimal are significant. Decimal. Here you have a decimal, so this is actually a significant digit. So this is a significant digit and this 1 is a significant digit. Between these two there are 2 zeros. Okay, so that's why we are counting them. And the same case over here. Anyways, that's rule 3 for you. And the last one, rule 4. And for some reason he doesn't want to change, so I gotta force him to change. There it is. And then you finally have an error that act as placeholders and they are not significant. So zeros at the beginning, some zeros like these, we completely ignored them. I don't know why though. 100.000, here they are significant, but this is also similar to that 800, so that's why there are only 2 and 800 itself. Okay, so maybe we'll have some exercises over here. Okay, so you have 0.0073 and you have 100.0202500. Let's try some. 0 at the beginning, not relevant. 0 again, not relevant because they're on the left. So this should be 2. Here, all of them. 1, 2, 3, 4, 5, 6. Here, only 2. 3 over here. We're gonna ignore this. 3 over here again. 1 over here. And 4. I may get wrong, so let's see. Two, 6, 2, 3, 4. Oh, 4, because this is after the decimal, so you have 4. 1, 4. That was easy. Anyways, so that's how you do this. And now some English vocabulary. So you have the word accuracy, which tells you, okay, so 15.7.396 is 57.396, and this is accurate to 5 significant digits, not 5 digits, 5 significant digits, because the if this was 57 or something, then you would say, okay, 2 digits. We don't count the digits after decimal digits normally, but significance, yep, 5 digits. You already know how to calculate significant digits. And when you're talking about precision, then it refers to the number of decimal positions, the order of the magnitude of the last digit in a value. For example, you have 57, the number 57.396 has a precision of 10 to the power minus 3. Okay, so that's the idea. So far so good, easy. We're almost at the end. It's not necessary. Okay, now something interesting. True error. Is there something called false error? Well, not exactly, but there is something called approximate error. True error is something that is accurate, and accurate. For some, you just write this formula. True error is the true value minus approximate value. Okay, so what is the true error? True error is the difference between the true value and also called the exact value. That's the keyword. And approximate value. So let's see this example. You have f derivative okay, so let's continue. F of x 7e to the power 0.5x. H is equal to 0.3 and I find x at 0.2. So we have to find the approximate value by using this formula, and then we can also find the true value using this. So let's deal with this. So if you use that equation that was written over there, you mean this one, then you would get this value, 10 to the 10.265. So you put f of 2 plus 0.3 minus f of 2 by 0.3. For each f you have to use that formula of f, that is, 7, it was something like this, 7 e to the power 0.5 into 2. So this is for this one. Similarly, you can find out this and then divide it by 0.3, and then you will get this answer, 10.265. Now the way to get the true value is even more easier. Just use this formula. Right, easy. The true value from the above equation is 9.514. See the difference? It's almost 0.7 difference, and you can see that. And be very careful about this minus, because true error is true value minus approximate value. So this is the true value. So don't write 0.7506, and don't just floor it up and round it up to 0.8 or 0.7. Don't do that. Now we are on 330. We want accuracy and precision. So that was how you use true error and find true errors. And this is for another value. You can use that. Try, practice them on your own. If you face any problems, please let me know. I don't think you will face though. And there's something called relative true error. Relative, so it relates. You have the original true error divided by true value, which gives you the relative true error. Super easy, just use this formula and you will get it. Nothing to explain over here. And what is an approximate error? Okay, this is an approximate error. You have a present approximation and the previous approximation. That means you try it for different values. You try it for 0.3, we already did that. We got 10.265. And then if you do this for 0.15, then you will get 9.8799. So the present one is 9.8799 and the previous one is 10.265. This is pre. Both are pre. So you have to write prev and press. PRE is same for both. Oh jeez. Anyways, so that's 10.265, 9.87 minus 10.265, 9.8799, sorry, and you get minus 3.8942%. So see, it's easy. Relative approximate errors can be found out in the same way, except this time you will use the error and the present one. Okay, now you will find a lot of details like this in your book, which is this. Go there in this link. You do have the slides on the online TSR, and actually you have the book. If you just open the book, you will see all this and more problems to practice. Maybe 1 and 2 questions could appear from here, so it is important, but it's good to know. So thanks for watching. This is not my thanks, it's from the one who created the slide, but either way I want to thank you for watching, and happy surviving, guys.